Okay, welcome back again. We'll now have a talk by Mr. Francisco Campuzano on ocean modeling with MOHIT for operations. Francisco Campuzano is an oceanographer and numerical modeler at Plus Atlantic Collab. He was formed in the University of Las Palmas de Gran Canaria in Spain and holds a PhD in environmental engineering from Instituto Superior Técnico and an MSc in estuarine and coastal management and science from the University of Hull. He was involved in more than 20 European and national research projects. He is co-chairing the ICESW GOOF working group and a member of 3 EuroGOOS working groups, IBRUS, Mongoose, and Coastal. He is a member of Copernicus Marine Service Champion User Advisory Group and member of several UN Ocean Decade Actions, and also steering committee member in Coast Predict and Ocean Prediction, DCC. He leads the EMODNet Physics River Node for providing near real-time river data. In recent times, he was involved in the development of oceanographic operational systems, linking watersheds, estuaries, and the open ocean. He has led several European projects of operational oceanography and environmental management, and is the co-author of 22 scientific papers and 16 book chapters. Thank you very much.
Thank you very much. Thank you very much for reading this. Well, good morning, everyone. Thank you very much. I will start with a big surprise for all of you. This is the presentation with no Julia line at all. Okay, so this will be a big difference from the rest of the presentation. So I see myself as a potential customer or user. I don't know if user, more customer probably. I'm representing some of the oceanographic community and the ocean community that is using some of the products. So what I've been doing my personal brainstorm during these last couple of days to see how I can use some of the things that are being discussed here that I'm very impressed, and I will be, in 1 year time, showing a presentation with sun lines of Julia. This is the challenge. So I will do an introduction about our group, a little bit of our group, and what we do, and what are the things that I believe that we could use Julia for. And also have a challenge for you at the end, to see if I can come back home with something that then I can put hands on, or try to put. I have also a couple of colleagues here, so I can ask them to put their hands on. So my name is Francisco Campuzano. Maybe I don't know if you get the name with this long presentation, and I work in Collab Plus Atlantic. That is an institution based in Portugal. And he has a very strong relationship with the Earth Center, and we are like our role is we are a non-for-profit association. So we have like 13 members. We have industry, we have also academy, and we have also national labs, and we are kind in between research and market. So the idea is to try to be something that develop further what are found in the universities. But we have these links to try to put all these groups together. Then we are new compared with many other institutions. We are like 5 years old, and now we have defined what are our main lines of activities and work. Some of them will be like supporting, all related with blue economy. I will tell you a little bit more about blue economy afterwards, but related with aquaculture and fisheries, we have applications with artificial intelligence too. We are moving also in meteorological and ocean forecast, and what is called now the digital twins. So we are working in this sense. And also we are providing some consultancy for the blue economy and try to build some tailor-made products. We have experts in artificial intelligence, numerical modeling, Earth observation. So many of the things that you were showing are very relevant to us. and we are a group of around 25 people. My colleagues, they say hello. They are colleagues of mine, so please also talk to them and try to involve them in the Julia thing. So why we do all our activities are mainly related with the blue economy and the coastal risk and management. So blue economy, for those of you that are not that used to the term, is a new name for something that is not that new. So like the economy is related to the ocean, so fisheries, aquaculture, ports, transport. I mean, there are some new things like marine renewable energy, deep sea mining. These are maybe new things, but most of them they were grouped in this sense, and they are like they need of information in the ocean to take the decision and to make some management, and they want information as accurate as possible, so then they can have a safer risk, safer coast from risk, like from floodings or apps or other kind of threats that we have. So basically, to do these forecasting systems, we need a lot of information. We use every single data that we can, and it's a lot of data. We use satellite data, even to find where are the fishing boats, to know the temperature, to know what we can observe. That also the satellites are limited to the surface, but then because of that we have also some floating buoys, gliders, many technologies. So this forecasting services is something that needs a lot of knowledge from many fields. So you need to know meteorology, oceanography, engineering, technological development, sensors, IT, data science, artificial intelligence. So this is a problem. In fact, we need to know and to talk to the different people with the different language and to use this. So the idea is that we put all this information and all this observation together in grids, and then we try to make forecasts out of it with models. So what are the models that we are talking? So some people may think that this is a good model, other people may think this is another good model. Some people may think I'm a model. Just to see now if you were awake, but this is not the model that unfortunately I'm not going to talk about today. I will talk about mathematical models and numerical models, that they have one advantage compared to the others. They improve with age, okay? So we solve bugs, we include new formula, and this makes that these models are more robust and that they can do other things that they were not able to do before. So the model that I will tell you about today, that we are using, is called MOHIT, that comes from the Portuguese Modelo Hidrodinâmico, but then it was supposed to be an aerodynamical model, but then evolved in something much bigger, and now it's a kind of a family of models that include one for the coastal area, one for the water sets, other one Lagrangian particles. I don't know if you are that used to this concept of Lagrangian particles, but I believe that you all know. And it's since 1985, so it's quite mature. It still has some pains from being that old, and tomorrow there will be some presentation talking about it. But it's also a software that has been developed. Of course, they have a promoting team, but then there are many users in the world. Like this is another institution that they have used or use the model. This is not an exhaustive list because we cannot know who is open source, so anyone can use. But this is what we find in the literature, who is publishing things using this model. And then they have this coastal model that is our open ocean model, storing that we call MOHIT water. This, of course, is the one that has more applications. normally more in Europe, less in the US. Maybe next year we can present more examples. But this is the most used. Even we have in all the continents. Okay, even in Antarctica we have one one implementation. And then this is the younger model, that is the Watershed model, but still is growing with time. So it's used for different things that I won't talk to you about it today. So it's even for precision agriculture or flooding events, rivers. So then this is built with a scientific background or with scientific production. So at the moment there are like around 130 MSc and PhD produced or contributing to the code, and more than 350 papers, journal and books. So we try to publish as much as we can or to document, but we know that it's not all as well documented as we would like to do. But then coming back to what we want to do in the coast and how do we use these models in the coastal area and in some particular areas. Normally we have these global circulation models. This is one example. That is from the Copernicus Marine in Europe. You will have something similar in the US and in other places, where you have a model that is covering all the globe, and sometimes you have regional models. You can download this data, this is all open access. But then when we want to go to the coastal area, we need to do something that is called downscaling. That basically is that we refine the grid step by step until reaching the desired resolution for the process that we want to study. So depending on the process, we will need, and we can do this many times. Like this is what we do sometimes, that just to extract one window of results, then we nest a model inside of it, then another, and they run separately. So this is one example for the Portuguese coast near Lisbon, where we had like 35 meters because we wanted to study the pollution from some freshwater source near the coastal area or bathing waters. And then we produce some indicators and we can produce some alerts with it. This is on the horizontal, how we reduce the scale, but also we have to take in consideration the vertical discretization, and we can do many things. It can be Cartesian, it can be sigma. Sigma is very common in some models, but then it doesn't work well for everywhere one kind of vertical discretization. So I'm trying to explain this because of the type of data you may find or Julia may find when we want to represent the data. And then I show you this example from mainland Portugal, but we can do for any other place. This is some configuration for Madeira Island, where we can go up to 200 meters, but 250 meters, but I think it was because also studying a submarine outfall. We couple different models, so we have hydrodynamic, we couple with the atmosphere, and then also with biochemistry, and here we can see just the image from top and a vertical cut next to the island of Madeira. And then we can do the same thing here also here for the Azores, that where we are. So I would like also to show you a couple of examples from here that we do in collaboration with the University of Azores. And then we go from this large resolution and we can go even to this small one that is the level 5 with 80 meters between Fayal and Pico. We also need these very nice graphics that you do. So we would like to start also using Julia for this type of application. But then if we go to a global model, that is the only available at the moment for the Azores, that is provided by a big institution, by a global entity, this will be the resolution. But if we want to go to this channel here between the island of Fayal and the island of Pico, this is one cell. So then we need to do this downscaling to incorporate this bathymetry that we were seeing here, and here you can see a bar. I don't know if you can see here the pointer, no? Not here, okay, but you can see like a bar in the middle, and this bar has a lot of influence of what happened. You can see it also here, and you can see it on the current. So for people that are crossing from Fayal to Pico by ferry, you can really feel this current. So this is the type of thing that we use this MOID model to solve some of the different resolutions. And then a different thing that we are trying to promote is changing the way we see the ocean, because normally oceanographers try to look only at the ocean and try to forget about the rest. This is how an oceanographer will make a plot, probably with Julia. But then the idea is that to integrate the whole Earth and move into what is called the Earth system models. So the idea is that we can integrate the watershed, estuary, and open ocean, and as the water continuum, as is also known. But we have several constraints or interfaces that we have to solve them properly. But just to show you how it would be a graph from a watershed model and how it works. Basically, it collects the water that comes from the atmosphere, and then through some streamlines, it goes into some channels. So this is some of the things that we graph that it will be also interesting for us to do with some of the packages or some of the code that you have. And here I'm showing one example for a dam in mainland Portugal, but also in the island you can have this effect, like today is raining here, but you can see an example of what Alexander was showing before of a real one of the I don't remember the name. The Von Karman stream. You can see it with the Madeira Island. So the island has an effect on the atmosphere, and then you have rain. So and then you can have this application also with rain going into outside of the continent. And normally, when you think about freshwater contribution, so then we want to do all these things in forecast mode and automatically or operationally, how it is also known. And then we divide this in, I would say, 3 steps. One is pre-processing or finding the data sources, interpolating, making the data available, making everything in the right format, looking for different sources, downloading, all this stuff. Then we run the models. It can be different models. It can be the MOID water, that, as I told before, or the water set that is called MOIDland. But also we can run WaveWatch from NOAA for waves, and we produce HDF5 files. This is our native format. And then we have the post-processing, where we distribute all this data and we do many things with the results. So we can go to a thread server or with OpenDAP, and then we have to convert into NetCDF. So this is another format that I know that you are all probably more used to work with it. We use this data for validation and to compare. We distribute in many ways. It depends of the end user of our product. So this is where I see Julia. I see Julia in the post-processing, doing graphs, or doing other application. I will show you some of the graphs that we produce normally, or some of the graphs that are required to us. And also in the processing, because before you go into this operational mode of forecasting, you need to test the model. And you need to be sure that the model is producing the result that you want. And only for you to understand how an operational model runs, basically every day you have a new forecast. It's like the weather forecast. You are used to work with it. No? So every day, probably the people that are operating the meteorological forecast, they are assimilating the data from yesterday to have the best result possible, and then they try to solve the forecast for the future with the equations, now also with artificial intelligence, but they try always to improve the hindcast with this. And this will be like, for instance, how the Copernicus global model works. Every 15 days, they do the best analysis, then an analysis, and then every day they move forward 1 day. So every day you have more day. So how we were doing this thing before? Surfer, MATLAB, ParaView also, other software. Now we are moving to Python, but we are starting, so this is why it's a good timing for talking to us and say, yes, why don't you try Julia? Okay, so it's a good timing for this. And this is, but we don't want to use, especially MATLAB for operational. Normally I get this error message because they cannot contact with the server and everything stops. And this is not very good for operational. So this is some of the graphs that we produce on a daily basis, especially the ones on the left. So these are the forecasts for today, we have different scales, as I was showing you before. So this is for the Portuguese economic exclusive zone. Not only, there are also other territories on it. This is our larger model. One for mainland Portugal, and this is for the Tagus story. And then also we produce other type of plots that are vertical cuts. And then sometimes we don't want to have a regular vertical grid because the biggest change takes place in the upper layer. So then we don't want to have a graph that is represent in the same size 5,000 meters than on the surface. So this is one of the things that is served for checking if the model is all right, but also we need to show this kind of information and to analyze the results. This is in an estuary in Sado, that is next to Lisbon. And this is another type of graph that we produce. We produce this kind of animations that I believe that we have seen many here. But you can see another particular thing here is that we have tides. So we have intertidal areas that cover and discover. Okay, so the grid may change with time. And then also we would like to plot like a line on it, and then we use this also for validation. The results are pretty good, in my opinion. We didn't do any assimilation or any trick on this, and we were quite happy with the result. But then we can do this for different properties, okay? So that was for temperature. This is for salinity. And so this is something that we produce on a regular basis. And this is more like analyzing the modeling results. Another type of analysis that we do generally is like validation or comparison. And here you can see on the left, this is a month comparison between the satellite that was Moore, that is 1 kilometer sea surface temperature, with the modeling results, and then we do cell by cell correlation, bias, root mean square error, and try to see how it moves. But we do like this integrated in 1 month, and on the right, this is just for one day, because we have just one file per day. As you can see here is the validation between the satellite is on the left, and the model results is on the right. On top, the ones that we produce. On the bottom, the ones that are produced by the global model. So we use also to compare how our model compares to the satellite, how the model compares to the global model that we are using for forcing. Then, as I said, we are also looking for data. We try to analyze all the possible data. So this is another type of data that we use. This is called Argo floats. I don't know if you are aware of this. So it's kind of a sensor that it has like a 10-day cycle. It drifts in the ocean for 10 days at the depth of 1,000 meters, and then it goes down up to 2,000 meters, and then on the way up measure temperature, salinity, oxygen. It depends on the technology. Now they are developing more coastal ones, so they don't go that deep, but they are also developing like deeper ones. So this information, there are thousands of them in the ocean. That is what also fits the global ocean models. And we need to compare our vertical profiles with the vertical profiles that are coming from this type of technology. And we need to do this kind of Taylor diagrams, this kind of temperature salinity diagram, this vertical profile diagram and compare between them. And then we have other technologies, like this is a glider. Then it's different because then we are operating it, so it's moving. This is a mission that we did here in the Azores, next to Fayal, and then you can see it doesn't go to the same depth of the time, and then it's moving in location. But then we need to compare this data also with the global model because we want to do how we perform, and also with our results for this area. And there are others that I won't talk about, like HF radars, that you have currents on the surface. So we are always looking for all the information because it appears that there is a lot of information, but there is not that much. And then other type of product or graph that we do is when we talk about these Lagrangian models, that Lagrangian models are like, instead of having a grid, you are following small volumes of water. That the volume of water, or it can be a volume of water, or it can be different stuff. It can be a container that is drifted by the ocean, and this type of technology is very useful for search and rescue operation, for oil spills. So I will show you one example here from the Prestige accident in 2002. This one of our first forecast, because it's 2002 operational oceanography was still, giving first steps. And we compare with satellite images, and the model results are pretty good. This for the time, we lost money because our server were not ready to provide so much information in real time, but then we recovered because we were able then to be involved in many projects related with this. And this is one of the latest version that we have from the Lagrangian model, and we use it for marine litter. Now that is kind of a hot topic, so we can put so many rivers, 61 rivers discharging, and then because it's the main entrance of marine litter, and then try to see where each river, marine debris from each river will go, which are the area of influence of every river. So we can identify river by river, and then we can perform this model was reshaped and is very, very efficient in terms of computing. We are running this sometimes in laptops or things like that. So you don't need a HPC for this model at the moment. Other way of doing this or graphing this is like, instead of putting the discharge from the rivers, it's like putting all the data or filling the Atlantic Ocean with these Lagrangian tracers and see where they tend to accumulate. Okay, so this, for instance, we can see that mainland Portugal, we don't have a big problem. Probably in the US and the Caribbean, they have a bigger problem than us with this. This is, and then when we want to represent, it's more not to analyze the result, but we want to represent sometimes what you can see behind are the currents, and then each particle with the origin. So this is the type of information that we use. But when we go sometimes to policymakers, they don't want this information like this. Yes, this is too much information. So we want to integrate this information into a grid that we have defined, and we want this in a shape file because it's what we use. We don't use NetCDF. NetCDF, what is that? So they want to move into shape files, so we need to deal also with other type of formats in order that we can provide this information. This is another example that we would like sometimes to integrate in polygons. Like this is one example also from the Azores. There is a marine protected area, and they want to know the temperature in the surface or 1,000 meters or just along the bottom layer. Okay, so it's looking for what is the first cell of water and representing all along. So it's not one layer of a grid. It's looking for every cell, the volume. And then, as I said, we produce sometimes NetCDF that go to thread servers, and then we can make this, we can distribute the data in this type of format, WMS, and it's very nice because you can see the streamlines and everything, but This is good depending on the end user. This is, if we have a control room like this, it's a very nice platform. You can play with that. But sometimes we are working with people from aquaculture. So this is their office. I don't expect them to do many clicks on the platform and to select properties and everything. So then we have to prepare the information in a way that is readable and easy to understand. So then we process the information in a way, I won't give you too much detail about this product, but we have set up this kind of graphs that are summarizing all the information, and then we can distribute it through Telegram or through WhatsApp, and then they receive it on the mobile phone. They don't need internet anymore. They don't need to click, and the idea is to concentrate all the information that they have into one graph. So this is something that we need in terms of production. So this is the kind of example of the type of things that I can imagine, and I imagine doing this personal brainstorming during this couple of days, that we could do also with Julia, or that some of them we can start little by little. But as I said, I have a challenge for you. Because numerical models, and now you all learn that, improve with age, but support tools get older. And this is a problem. Because then you develop something that works for Windows or for Linux, but it works for Windows 7, not for Windows 10. Everything is changing all the time. And also Linux is changing all the time. Everything is changing all the time. So support tools are very difficult to maintain, or is a bit expensive to maintain. So my challenge and offer is that, okay, coming back to the first presentation on Monday about if you develop something during 5 years and then the person at the end doesn't want it and you invest thousands of dollars or euros or millions or whatever, in this case, the community of the end users, we know what we want, okay? So we won't change that much what are our requirements. We know, as you can see, what are the type of graphs or the type of tool that we want to produce. We know what are our formats, and you don't need to program something that is able to read now a value, now a name, now a vector. No, it will be always the same. It will be always the same file with different information, structured in the same way. Very boring, probably for you, but it will be the same. But so there won't be this waste of time and money and resources on using user and developer feedback, and the user satisfaction will be guaranteed. Also, we can also provide this access to the modeling community. So if we start producing something in Julia, in this sense, we can also distribute it along with the model binaries and code, and then this may be an entry for other people that are working also with IT into practical programming with the Julia. So at the end, you will gain more Julia users, which I believe that is a jackpot for you. So I'm going to show you what is the tool that I want to replace, because now it works randomly. Some computers work, others don't, because of the graphic card or because, okay? But I will show you, and I will show you the capacities, okay? So I'm going to open one file, HDF5. I can choose one day, it can be the day of tomorrow. And then when I open, and I do this on a remote computer because my laptop doesn't work, okay? So it's a real need, I'm not making it up. And then I select what is the latitude, and of course, the code will be. And also I was thinking about this yesterday when I seen some of the presentation like Mikey, that you have also buttons and things like that. I mean, it doesn't need to be a self-contained software, but it could be one of the. And then we can also put the vertical profiles, and then we choose, okay, we show temperature. And then we select the time, and then we run. Okay, so we can select the color, and we can normalize. And so it's between 0 and 1. Up, to make it bigger. Okay. We can zoom. We can pan. We can change automatically, like, okay, instead of normalize, I want temperature between 10 and 20. Okay, so this is very useful for us because when we are starting a model, if the model breaks, have a problem or anything, we need something quick. It's not for making an image for a publication in a journal. Even, I mean, it's not that ugly. But this more for something that is rapidly opens, then I can analyze, then I can see, okay, what is happening? There is a problem in the top layer. Okay, I will see the top layer. No, it's not the top layer that the problem was. Okay, so I want to change the region of interest. So instead of being this cut, I will do another one below. And then I can see here, okay, but now this seems okay. So I will change that one, and I will put more near to the bottom. Of course, you can see here is recognizable, but you can see here some sea mountains. So it's doing this vertical cut, but we can do vertical cut, but we can do also, we can select, instead of horizontal layers, we can, this vertical cuts, okay? Then I can change the relationship between X and Z, because if not, I won't see anything that is properly understandable. Oop. Maybe it's too much. I will leave it like this at the moment, okay. Okay, well, doesn't matter. I have one open here also. What is the best we can do? Even we can do like 3D and add in different layers. So we can rotate. You can see the bathymetry here. I mean, it's similar to things that I've been seeing here. I mean, that's why I believe that this may be easy for you. If it's already uploaded on the Google Drive. There is an HDF5 file. Okay. So then, I mean, you can see that you can add layers. You can add horizontal layer with vertical layer. We can see on the 3D, and then we can also here. I mean, I'm not making the most complex of all, but we can put also Lagrangian particles here, so we could see how the particles are moving if they go from the bottom of the ocean to the surface. We could see with the instance how it works. So, and then I can move the time, change the scales. So it's interactive in the sense that it's not a plot for distributing for outside. It's a tool for analyzing for the modeler. So it needs to be fast. And sometimes when we use ParaView, we can produce very nice graphs, but we need to do many clicks, to see the file, which is. So we were thinking this is a tool that it was developed by this group in the university, but it's no longer maintained. And then we are trying to recompile it, so then we can keep using with the new versions of Windows, at least. But it's not being very easy. So at the moment what I do is that I know some computers where it works, and then I use it there, and I don't use it in my laptop, for instance, which I know that it's not the best practice. So that's why I bring you the challenge, because what I have seen in your presentation is not very different from this. Okay? Then I was thinking about it while I was doing this personal brainstorming, and talking also with people from Air Center, say, maybe Thursday afternoon in the expert hour, we can try to talk about it a little bit and try to put some, because this, that would be very, very helpful. And I understand from your presentation that this is probably not the sexier thing that the Julia can do, but it's really a very useful tool for us. So I leave the challenge for you. Maybe tomorrow we can talk at any time. I'm here for that. But also, if you want, we can tomorrow in this expert hour we can talk more into detail. But if you want any detail before, or you have other ideas or how we can do this, I'm very happy with that. And well, that's everything I have to tell you. If you have any question, that's it. Thank you.
I do have a more technical question regarding how you did the ocean modeling. Did you do, is it like downscaling from the Ocean Copernicus service? Like you took the data from the Marine Copernicus service and then downscaled it to fit like around the Azores for your ocean modeling?
The microphone doesn't hear.
Sorry, I just wanted to ask. I just wanted to ask for like how you did the ocean modeling, because I'm interested in that as well. Like, did you use like open boundary conditions, and then after that data used for open boundary conditions was from the Copernicus service? Yeah.
So yes, I can explain you more about how we do the modeling. I didn't go too much into the details. But yes, basically what we do is, our recipe, that we take these global models, we put it on the open boundary condition that you can see in this case is all these areas and then we relax this result inside of the model. But then we have meteorology. So sometimes we use GFS from NOAA. But sometimes we use IPMA, high-resolution models, depending on what we have. And then we also look for river data, that it can be from a model, it can be from observations, and then this generates the solution inside. In this model in particular, is running free. So we have all the equations working and that. But some other people do more assimilation, so they refresh the values inside of the domain after a certain period. But yes, what we do, this downscaling thing, is to go from these global models, use them as boundary conditions, and go into the coastal area.
Thank you.
Welcome.
Super nice presentation.
Well, thank you very much.
My question is, how confident are you applying this downscaling assessment from the global model to the Azores? Because it is one thing that it has been really hard for us to try to work with these global models, because there's none for the Azores.
Yeah.
No regional models. So how can improve, or how to improve?
Yeah, the best thing is to have more data. This is always like a good bathymetry always helps, high resolution bathymetry, and also observation. And we were last year in Fayal during this course of with MIT, MIT Portugal is co-organizing a marine robotics course there, and we have some validation there, some direct and some indirect. The direct one was like, okay, we found that there was some tidal ghosts. We compared with the model result, and they were very nice. Very, very good. The indirect one, there was one guy with a wave glider that had to come back because he has a problem with communication. And the guy was in the same place where we were, and I was telling him, look, take care. If you want, and I think you can even see here in the figure. So this is the port, it's just in the southwest. Okay, this entry there where there is this mountain. If you want to enter here, you better go by Pico, because the current is very strong up. So then you go up and then you go down. He didn't believe me, so he tried to go direct and has to cancel because the current. So then there was also, and I was telling him, okay, look, this is the best timing, the best time of the day, and if you want to do this, I will do the operation this way. And then maybe he received other instructions, but then he tried on the approaching the coast from the other direction, and he has to come back. And then he managed afterwards. I said, he came. You were right. Yes, I don't want to be. Yeah. So, but the comparison that we are doing, of course, we are trying to collect more data because it's important, the quality of the data. But we have done this in many places, and the results are. The better the information that you have, the better the result. But in general, it works well.
The institute that you are using, talking about satellites, but for example, for the water column, are only from a few points, right? Because there's not a lot of information.
Yeah, that's why I said that we are unfortunate that we have to understand everything, because we are looking for remote sensing, tidal goals, whatever kind of information, ferry boxes, like ships of opportunity, whatever people that goes out there and collect data, we are always looking for data to compare, because in some places, even if we are sometimes close to the coast, and there are estuaries where there are no observation in near real time at all. So then sometimes we have to look for historical data, simulate that period in particular, and sometimes even, and then we have other problems that maybe also with that there may be other problems also with the meteorological forcing. Imagine that we don't have a good meteorological forcing in the area, and the meteorological models has their own errors. So, but in general, the results, they are. I mean, the comparison that we did, they were very good. So, okay, thank you very much. So I will be here until Friday if you want to make me a surprise.